Welcome to the NPTEL MOOC on Discrete Mathematics. This is the second lecture on set theory. At the end of the previous lecture, we were discussing functions and relations. A function we saw is a relation such that for every x belonging to the domain of the function, there is a unique y in the range of the relation so that xy belongs to f. This would be the range of f. For every x belonging to the domain of f, there is a unique y in the range of f so that xy belongs to f. So that is what a function is. Since an x has a unique mapping in the range, the image of x can be denoted as f of x. This is the image of x under f. It means x f of x is the only ordered pair with x as the first component and belonging to f. We say that a function maps a into b, where a function is from a to b. We said that function f maps a into b if the range of f happens to be a subset of b. We say that a function f maps a onto b if the range of f is equal to b. So if f is a mapping onto b, or f is a mapping onto b, then f is a mapping into b as well. We said that a set R is single rooted if and only if for each y belonging to the range of R, there is a unique x so that x r y. Even a non-relation can be single rooted. For example, consider this set. This is single rooted. For every ordered pair belonging to this set, that is, we consider 2 0 and 2 1, and consider the second components. 0 and 1 are the second components. Each of them has a unique pre-image. The only pre-image of 0 is 2 and the only pre-image of 1 is 2. Therefore, this is a single rooted set. So, single rootedness can be a property of a set. A function is called one-to-one if and only if it is single rooted. So, if the function is from set a to b, for each x belonging to the domain of the function, there is a unique image y. That is because it is a function. Now, since it is single rooted, then y has a unique pre-image x. So, each x in the domain has a unique image y in b, and each y belonging to b, the range of the function, has a unique pre-image x in a. That is when the function is called one-to-one. So, a one-to-one function is a single rooted set. A bijection is a function that is one-to-one and onto. and injection is a function that is one to one, and into, but need not be onto. So, a bijection is also an injection. A surjection is a function that is onto. So, combining all these definitions, we say a function is a bijection if and only if it is an injection and a surjection. You must be familiar with these terms: bijection, injection and surjection. Consider two sets F and G. We define the inverse of set F, denoted F inverse, F to the power of minus 1. This is defined as the set of all ordered pairs UV such that the ordered pair VU belongs to F. That is, you consider all ordered pairs belonging to the set F and then invert the ordered pairs. Make the first component the second and the second component the first. The ordered pairs that you obtain will form F inverse. For example, if F happens to be 2, 0, 1, 0 and C, then F inverse is 0, 2 and 0, 1. So, F need not even be a relation for it to have an inverse. Even for sets we can define an inverse. So, to find the inverse of a set, you take out all the ordered pairs belonging to the set and then invert every single ordered pair. The restriction of F to A, denoted in this manner, this is called a restriction of F to A, is defined as the set of all ordered pairs UV so that UFV and U belongs to A. The image of A under F, which is denoted like this. The image of A under F, this is defined as the range of the restriction of F to A. This is the set of all V such that the X is U belonging to A so that UFV. The range of the restriction is what? The image of A under F. Then we have a number of theorems. I will not prove these theorems here. These are trivial enough for you to prove them as exercises. For a set F, domain of F inverse is the same as the range of F, and the range of F inverse is the same as the domain of F. Another theorem says, for a relation F, F inverse of inverse, the inverse of F inverse is the same as F, which is trivial enough. for a set f, f inverse is a function if and only if f is single rooted. That is, every element in the range of f has a unique pre-image. That is when f inverse is a function. A relation f is a function if and only if f inverse is single rooted. Say f is a one-to-one function. For x belonging to the domain of f, f inverse of f of x is the same as x, and for y belonging to the range of f, f inverse of y is the same as y. This is true for a one-to-one function. For two sets f and g, we define f composition G thus. It is a set of all ordered pairs UV such that there exists a T so that UGT and TFV. And then a theorem about function composition. If f and g are functions, then f composition G is also a function. If G is a function and G is applied on U, then it will produce a unique T. And if f is a function, when f is applied on T, it will produce a unique V. Therefore, f composition G will also produce a unique V for every U belonging to the domain of it. Thus the theorem. The domain of f composition G is all x belonging to the domain of G such that g of x belongs to the domain of f. For any two sets f and g, the inverse of f composition G happens to be the composition of G inverse and f inverse. So these are theorems that are easy enough to prove as exercises. Do attempt to prove them. So we have seen some basic definitions of set theory. Let us show that Peano system can be embedded within set theory. Russell and Whitehead proved that the whole of classical mathematics can be embedded within set theory. I'll give you a peek as to how to do this. So we will begin with Peano system. Peano system deals with arithmetics. We have already seen Peano's axioms in the module on logic. So let us see how to embed Peano system in set theory. First of all, for a set A, the successor of A denoted A superscript plus is defined as A union the singleton set containing A. That is, when you take a set and add it to itself, we get the successor of the set. So this is how the successor of a set is defined. And then we say a set A is inductive if the empty set belongs to A, and for every A belongs to A implies that the successor of small a also belongs to A. For every small a belongs to capital A implies that A plus also belongs to capital A. That is, the successor of small a also belongs to capital A. In other words, A is closed under the successor operator. So for a set A to be inductive, it should contain the empty set, and for any set belonging to A, it should also contain the successor of that set. That is, the set should be closed under the successor operator. That is when we say that the set is inductive. Now let us define omega as the intersection of all A such that A is inductive. We define omega as this intersection of all inductive sets. That is, X belongs to omega if and only if X belongs to every inductive set. Which is precisely when X belongs to the intersection of all inductive sets. So the definition says that X belongs to omega precisely when X belongs to every single inductive set. Now let us consider some interesting properties of omega. First of all, omega is a subset of every inductive set. That should be obvious, because in the previous slide we have just seen that if X belongs to omega, then X belongs to every single inductive set. Therefore, omega is a subset of every single inductive set. That is, the members of omega are members of every single inductive set. And then omega is inductive as well. Why should this be so? This is because phi belongs to A if A is inductive. For every A that is inductive, phi belongs to A. Therefore, phi belongs to omega as well, because omega is the intersection of every single inductive set. So if phi belongs to every single inductive set, it should also belong to omega. So that is the first requirement for omega to be inductive. It should contain the empty set. So it indeed does contain the empty set. Now consider some X belonging to omega. Then X belongs to every inductive set. But then all inductive sets are closed under the successor operator, which means X plus belongs to every inductive set. In other words, X plus belongs to the intersection of all inductive sets, which is precisely what omega is, which means X plus belongs to omega. So what we have is this: if X belongs to omega, then X plus also belongs to omega, which means omega is closed under the successor operator. That is the second requirement for omega to be inductive. The first requirement is that omega should contain the empty set. The second requirement is that it should be closed under the successor operator. Since we have established both, we know that omega is inductive. So omega, which is defined as the intersection of all inductive sets, is itself an inductive set. And once again, an inductive set is a set which contains an empty set and is closed under the successor operator. Suppose X is a subset of omega, and suppose X is inductive. But then omega is a subset of every inductive set. Therefore, omega is a subset of X as well. But since X is a subset of omega, this implies that omega equal to X. What it means is that if X is a subset of omega and X is inductive, then X has to be the same as omega. Or in other words, no proper subset of omega is inductive. So combine this with the definition of omega. Omega is the intersection of every inductive set, and omega is a subset of every inductive set, and no proper subset of omega is inductive. So in that sense, omega is the smallest inductive set. Every inductive set is a superset of omega. Now using this omega, we can embed natural numbers in set theory. So what we do is this: we define natural numbers in this manner, we construct natural numbers in this manner, we define 0 as the empty set, we define 1 as 0 plus, which is the successor of 0, which is 0 added to itself. Which is the successor of 0, which would be 5. That is because this is phi union the singleton phi. So 1 is the singleton containing phi, and then 2 is the successor of 1, which would be phi union the singleton which contains the singleton phi. This would be the set containing 2 elements. One is phi and the other is a singleton containing phi. This is what is defined as 2. And then the number 3 is defined as the successor of 2, the number 4 is defined as the successor of 3, and so on. So in this manner we define all the natural numbers. So you can readily verify that 0 is a member of 1, which is a member of 2, which is a member of 3, and so on. Not just that, 0 is a subset of 1, which is a subset of 2, which is a subset of 3, subset of 4, and so on. So both these chains of relations hold. So we have, in this sense, defined omega as the set of all natural numbers. Omega is the set of all natural numbers. That is because omega contains 0, it contains a successor of 0 which is 1, it contains a successor of 1 which is 2, and so on. For every set, it also contains the successor of that set. It is closed under the successor operator. So we define omega as the set of all natural numbers. And then you would recall Peano's axioms that we saw in the module on logic. We define addition in this manner: a plus 0 is a, and a plus the successor of b is the successor of a plus b. Similarly, multiplication is also defined. Multiplication is defined thus: a into 0 is 0, and a into the successor of b is a into b plus a. So, multiplication is defined using addition, and addition is defined using the successor function. So, in this manner we can construct natural numbers and the two operations addition and multiplication. You can verify that once we define numbers in this manner, then all of Peano's axioms will be satisfied. Suppose we have a one variable predicate alpha of n. Suppose we want to show that alpha of n is true for every n belonging to the set of natural numbers. We can define T as the set of all natural numbers so that alpha n holds. Suppose we prove that T is inductive. Then we would be done, because the smallest inductive set is omega. And omega is the same as the set of all natural numbers. So, once we show that T is inductive, we would be done. Suppose, for example, we want to show that every natural number except 0 is the successor of a natural number. Suppose this is what we want to show. Then we can define T as all those natural numbers that are either equal to 0 or are successors suppose this is what T is, and then we want to show that T is inductive. So, this is the question we have: is T inductive? To prove that T is inductive, we have to show two things. First of all, we have to show that empty set belongs to T, but empty set is the same as 0, and 0 certainly belongs to T, because T contains all those natural numbers that are either 0 or are successors. So, 0 is explicitly included here. So, 0, which is the empty set, belongs to T. So, T satisfies the first requirement. Then what is the second requirement? The second requirement says that if P belongs to T, then P plus, which is n, also belongs to T. That is also satisfied. Therefore, T is indeed inductive. So, T is an inductive subset of the set of natural numbers, but we have just seen that there is no inductive proper subset of the set of all natural numbers. Therefore, T must indeed be the set of all natural numbers. So, this is a property that is satisfied by the set of natural numbers. Every natural number except 0 is a successor of a natural number. So, this is how we embed the set of natural numbers in set theory. A relation R on a set A is called reflexive if x R x for all x belonging to A. A relation R is reflexive on a set A if x R x is true for every x belonging to A. Similarly, we say that a relation R is symmetric on A if x r y implies y r x for all x y belonging to A, and a relation R is transitive if for all x y z belonging to A, x r y and y r z implies x r z. When a relation satisfies all these three properties, a relation that is reflexive, symmetric and transitive on set A is an equivalence relation on A. As an example, consider a set of natural numbers, and let us say two numbers are equivalent, that is two numbers are in relation R, x r y, if and only if x minus y is 0 mod 3, which means 1 r 4, 4 r 7, 7 r 10 and so on. These are all 1 mod 3, 1, 4, 7, 10 etc. are 1 mod 3. Similarly, 0 r 3, 3 r 6, 6 r 9 and so on. So, since 0 r 3 and 3 r 6, by transitivity 0 r 6 as well. We also have 2 r 5, 5 r 8, 8 r 11 and so on. So, the equivalence classes in this case would be 1, 4, 7, 10, 10, 16 etc. This is one equivalence class. 0, 3, 6, 9, 12 etc. will form the other equivalence class, and the third equivalence class would be 2, 5, 8, 11 and so on. This corresponds to numbers that are multiples of 3. These are numbers that are 1 mod 3, and these are numbers that are 2 mod 3. So, this relation has 3 equivalence classes. An equivalence class of R is a maximal subset of A such that any two members of it are in relation R to each other. So, the equivalence class containing X will be denoted thus. Formally, this is the set of all T such that X R T or T R. By reflexivity, you might as well say T R X by symmetry. The quotient A with respect to R is the set of all equivalence classes under R. Formally, the quotient of A with respect to R is the set of all x R such that x belongs to A. Let us see how the theory of integers can be embedded in set theory. Let us consider ordered pairs of natural numbers. If Mn is an ordered pair, we would like to associate this ordered pair to the integer m minus n. For example, 2, 3 can be associated to the integer minus 1, whereas 3, 2 will be associated to the integer plus 1. So, we would map ordered pairs of natural numbers onto integers in this fashion. For this purpose, what we do is this: we define a relation on natural numbers. This relation is defined in this manner. We say that ordered pair Mn and Pq are in this relation if and only if m plus q is the same as n plus p. Of course, we would have wanted to say that m minus n is equal to p minus q, but we can't say this because the set of natural numbers is not closed under subtraction. So, m minus q may not be a natural number. But of course, from our arithmetics we know that if m minus n is equal to p minus q, then m plus q is the same as n plus p. So, using additions, we are effectively saying the same thing. So, this relationship is an equivalence relation on n cross n. That is because this holds reflexivity. Why would this hold? That is because m plus n is equal to n plus m by commutativity of addition of natural numbers. So, reflexivity holds. For symmetry, we require that if the relation holds between Mn and Pq, then the relation should also hold between Pq and Mn. If the relation holds between Mn and Pq, then we have by definition m plus q is equal to n plus p, which by commutativity of addition, or which implies that n plus p equal to m plus q, which would imply that Pq is equivalent to Mn by the commutativity of addition. N plus p is the same as p plus n and m plus q is the same as q plus m. Therefore, Pq is equivalent to Mn. That is, Pq is in this relation tilde under with Mn. Therefore, this relationship is symmetric as well. And then you can verify transitivity if Mn tilde Pq and Pq tilde Rs, then you can easily verify that Mn tilde Rs. So, transitivity also holds. Therefore, this is an equivalence relation. Then using this equivalence relation, we can define integers in this manner. Let us define the set of integers z as the quotient of n cross n under the tilde function. So, what exactly do we do here? We define integer 2 as the equivalence class that contains 2 0, the equivalence class under tilde which contains 2 0. This would of course contain 2 0, 3 1, 4 2. This is a set, and it would also contain 1 minus 1 and 0 minus 2. So, in particular on the xy plane, if you consider the integral grids and consider a line of slope 1 which passes through 0 minus 2, all the integral grid points that fall on this line will form the set. So, this set is what we define as integer 2. Then what would integer minus 3 would be? That would be the set of all pairs which are equivalent to 0 3 under this equivalence class. That would be all the integral grid points that fall on 0 3, the line with slope 1 and passes through 0 3 will define this equivalence class. For example, 0 3, 1 4, 2 5, 3 6 and so on. This is what is defined as integer minus 3. So, we can define integers in this manner as equivalence classes under this equivalence relation tilde. And then we can define the operators on integers, addition and multiplication on integers appropriately. So, using this device what we do is to define each integer as a set, and then operations addition and multiplication that work on integers would be defined as operations on these special sets. If the operators that we define behave in a manner which is exactly mimicking of the addition and multiplication operations on integers, then we would be able to say that we have embedded the theory of integers on n cross in set theory. So, that is precisely what we will attempt to do. The details we will work out in the next class. That is it from this lecture. Hope to see you in the next. Thank you.